My name is Jonas and I welcome you to this video where we will look at best practices for implementing the hardware abstraction layer in EEROS. In fact, most of it is already implemented in the EEROS framework and we only need to specify certain transmission factors. But let's get started. You may ask, what is a hardware abstraction layer? Well, basically, it is an interface between EEROS and the underlying hardware via a hardware wrapper library. Or in other words, it describes the available hardware and its properties along with the necessary libraries to access the hardware. In our case, the underlying hardware is the BeagleBone Blue, but it could also be any other platform. And the great thing about the hardware abstraction layer is that you don't have to rewrite all your software when you switch to another platform. All you have to do is rewrite the hardware wrapper library and you are good to go again. A list of supported platforms can be found on the EEROS wiki, as well as instructions on how to write your own hardware wrapper library. The link to the wiki is in the description. On the BeagleBone Blue, we can drive the onboard LEDs, read out the buttons and GPIO pins, control up to 4 motors and measure their position with encoders, set the position of up to 8 servos, read out analog inputs like the DC check or the battery, or capture data from the 9DOF IMU and the barometer. All inputs and outputs can be either digital or analog, with the exception of the encoder, which we will come back to later. Digital signals can only take 2 values, while analog signals can take a variety of values. In the hardware configuration file, we can set the range and scale of an analog signal so that its digital value matches its analog value. Using a motor as an example, we will now learn more about the range and scale parameters. The motor drivers of the BeagleBone Blue accept a duty cycle between -1 and 1 as an input, with -1 representing full reverse and 1 representing full forward. However, if we want to control the motor, we want to set the voltage of the motor, not just a duty cycle. One option would be to manually calculate the duty cycle from the voltage, but this is not necessary in EEROS as the hardware abstraction layer can do this for us if we set the scale and range of the signal properly. Let's first look at the scale. The scale describes the relationship between the digital value and the analog voltage according to a concrete measurement. So in the case of the motor, it describes the ratio between the set duty cycle and the output voltage of the motor driver. To set the scale, we can set a small duty cycle and measure the voltage. We can then enter this duty cycle as min in and the measured voltage as min out under the scale section in the hardware configuration file. Then we repeat this process with a large duty cycle and enter this duty cycle and the measured voltage as max in and max out. Now that we have set the scale, we must also set the range. The range describes the relationship between the digital value and the analog voltage according to the datasheet. As with the scale, we need to enter the min in, min out, max in and max out values to define the range. However, this time we take the values from the datasheet instead of setting a duty cycle and measuring the voltage. Here we can see an excerpt from the hardware configuration file of the BeagleBone Blue that we received with the template project. The max and min values are already set correctly and only need to be changed slightly, if at all. As already mentioned, the encoder is an exception. It behaves similar to an analog signal, but can rotate forward or backward without limitation. To configure an encoder, we take its resolution from the datasheet and enter this value as max out and 2π as max in the scale section. For the range, we set the no limit parameter to true. Remember that we have a quadrature decoder. So if we have an encoder with 16 ticks per revolution, then the resolution is 64, which is 4 times 16. But what if our motor has a gearbox and we want to know the position of the output shaft and not the position of the motor? In this case, we can define several scales and ranges in our hardware configuration file. EEROS will then calculate the scale and range of the whole chain for us. This way we can map our hardware directly in the hardware configuration file and enter meaningful value instead of a total transmission factor, which we won't know what it actually means later anyway. Please visit the official EEROS wiki for more information about EEROS and the hardware abstraction layer. The link is in the description. Thank you for following me through this overview and implementation guide, and I will see you in the next one.